Hey, what are you doing over there? The show's starting.
Hey there, welcome back to another episode of College Unfiltered Opinions. I know it's been a long time, probably the last upload was 10 months ago because I had some personal tasks to deal with, and nevertheless, we are here for another episode. Yes, what do I mean by we? So, today we have two guests. Probably this is the first episode that we have two guests over here. That would be Shreyas Pai and Shrish Bajpai. They are my good friends. We are in the same class, and you guys introduce yourselves.
Right, so I'm Shrish, in the same class as Golis, a good follower of this podcast, and I'd also like to point out probably the first time we are stuck with just one host. So I hope he'll be able to handle the two of us.
I'm Shreyas Pai. Everyone calls me Pai because Shreyas.
Okay. And you're in the same class, that's it.
Yeah.
And one more thing, Srini couldn't join us today because he has a music club orientation. Best of luck to him and hope that goes well. So, guys, what are we going to do today? Probably this episode will be titled Quantum Computation, Grover's Algorithm, and Quantum Phase Estimation. So, before we start, I would like to. Is it give a disclaimer? Do you give a disclaimer or do you?
I think it's you give a disclaimer.
Yeah, so I would like to give a
I mean, the disclaimer we are about to give nullifies what we are going to tell anyways, but
Okay,
still.
but yeah, I would like to give a disclaimer saying that do not use this episode as a research for your project or don't use this as a study material basically. All we are trying to do is make you curious enough to do your own research after this podcast, and just at the end of the episode, just be curious enough in this topic. That's all we are trying to achieve here. And one more disclaimer would be preferably don't listen to this casually or while you're doing some other task. It'll be hard to follow. And that's it. And this episode is particularly difficult because look, it's quantum computation, and I will try my best to keep the maths to a minimum, and we'll take a storytelling-esque approach and probably keep the attention. Okay, so in PS we have this system, we have this elective system where luckily we get to choose what we want to study, not for the whole semester, but 8 credits. You get to choose 8 credits per semester, and we had a lot of topics. I chose what was my E4? I chose operational research. That's where you basically solve like traveling salesman problem or try to find the best route into traffic or something like that. That's the application of OR. But Shrish and Pai here chose what was your elective's title? The name of the thing?
Quantum computing,
Yeah, the title of the course was quantum computing.
quantum electronics, and quantum computing to be exact.
Quantum electronics and quantum computing. Okay, so they were graded a little differently. They didn't have like these traditional tests, but you had to submit a mini project at the end of the course, and they would be graded on that project. And once I read the project, I felt it was interesting enough to make a podcast episode on it. So here it is. Cool. Right. The title of the episode, Quantum Computation or Quantum Computing. Right. Quantum. What is quantum? Quantum is behavior of anything in a small environment, to be very rough. Right. And when you go to these very small scale environment, right? They don't follow classical physics, or they don't have the same variables or parameters as we are evolved to experience. So they follow different set of rules. Now, the reason, like, sure, like we have Marvel movies made on concepts like made on quantum concepts. And the reason why it's interesting is you get to play with different set of rules, non-classical rules, when you go to atomic or subatomic scales. So that's pretty cool. It's basically like
Counter Strike.
yeah, Counter Strike. So quantum is like it gives you the flexibility to play either as a terrorist or cop. So it gives you get to play with different rule sets. And once you go into the quantum realm, you no longer you work with different parameters, and there's a sense of difficulty in this because as I said, we are evolved in the classical realm where we are used to units such as meters, centimeters, kilometers, or kilograms, and we are used to Newtonian forces. But once you go into subatomic particles, the scale, you use a different scale, and the force causing, effect causing parameters are different. So again, different set of rules is basically the underlying point which I wanted to make there. You want to add something? Just it's a conversation. Just tell.
So before we go any deeper, I'd like to put out a disclaimer of my own. That is, as we go deeper, some of you who know, some of you who don't will start to understand. It's very hard to describe anything to do with quantum mechanics or computation without math after a certain level. Because if you think about it, understanding can only take you so far, because there are a lot of concepts we use which we can't really explain. The math just works out the way it does. And that is why you must have heard that quantum is very bizarre and very different and stuff like that. One more thing I'd like to add is not that well today. My voice might be a little shaky here and there. I hope that will be compensated by the topic we are going to discuss. So if you think about it, as to what Gola said, working in very small domains, a better way to approach it, in my opinion, better in sense of understanding, not science, would be to think about how much can you break down something. You start with something, let's say you start with a pencil, you break it into 2 pieces, you break it into 4 pieces. At some point you're just left with the wood, so you start breaking apart the wood, and then you're left with a powder. Maybe it's just molecules, you start breaking it into atoms. So at some point you do have to stop, and wherever you define that point to be, earlier it was known to be as molecules, then an atom at some point, maybe quarks now, and I don't know if we'll get any smaller sometime soon. But the point is, wherever you decide to stop breaking particles is where you start working with quantum mechanics. Because the biggest difference between classical mechanics and quantum mechanics is not that classical mechanics doesn't exist in the quantum realm. It just doesn't remain that important. And the reason why it's so hard to understand and why we need a lot of math is because everything at the quantum level becomes a game of probability. So if you take a ball right now and you drop it, you know there's a force that's pulling it down. You can see the ball going down. The ball will hit the floor. It will bounce up a distance. You'll have some sort of intuitive understanding. Looking at a ball, looking at the floor, maybe you'll have to tap it a couple of times, but you can tell how high it's going to go. But that's not how it works in the quantum domain. No object has a particular position or velocity. You must have heard this in Heisenberg's uncertainty principle, I think. That was it, right? That talked about position and velocity. Yeah.
Heisenberg.
So basically every object exists in a probability space. So you may not find it, you may find it, but the only way to decide is to actually go there and find it. So we don't define objects as locations, we just define them as probability of maybe it will be here, maybe it won't. And if you think probability is easy, wait till you get to quantum, I suppose.
There's a theory that the act of finding it also affects the probability of finding it, right?
That is again with Heisenberg's uncertainty principle.
Okay, that's uncertainty.
Because you can only know one thing accurately. So if you know the absolute position, you can't figure out velocity, or the other way around. So there's a lot to do. Where do we start?
So conducting quantum experiments, so basically all the college level experiments, quantum experiments are conducted in simulators, where it's just like running virtual machines, right? So when you simulate Raspberry, is it? Like how you
Yeah,
sell it,
sort
like
of,
just
most of it.
yeah. So like how you simulate Raspberry Pi's environment in a virtual machine, you would probably simulate a quantum schematic in a quantum simulator, where which gives which removes the problem of accessibility. But again, there are different constraints, as these simulators can handle up to, like, let's say max 20 to 25 qubits quantum width, which will come back to what it is. So would that be a hurdle in real life, the fact that you can only handle 20 qubits, or like are most of the applications handled in those 20 qubits?
I mean, before we go there, we need to understand where exactly quantum computers have, superiority over regular computers. So just telling quantum computers are better is a very general term, and it's not really true. So going, let's say, 50, 60 years down the line, you have a quantum desktop that's not gonna game any faster than your regular desktop. So the advantage a quantum computer basically has is in computational tasks that require a lot of parallel computing, or parallelism as we call it. Quantum computers pull far ahead because of qubit. So I mean, we'll get into qubit at some point. I don't know if this is the right time to delve into that. But yeah, so the issue with modern day quantum computers are they work at a very low temperature. So this is computers that are not simulated. So if I'm not wrong, IBM does give access to actual quantum computers for people who want to code it out. So they have their quantum computer in a lab set up somewhere, and everyone can sit in a queue and remotely tap in and work on it. At the same time, there are libraries like Qiskit that let you, simulate stuff on Python itself. But the fact that there are 20 qubits, it's enough to explore, because right now we are again at the same point where we are beginning to understand what we can actually do with quantum computers. And the process is not as fast because there isn't an intuitive sense as to how things are progressing. We require some amount of math which makes sure that it's accurate to an extent, but at the same time it takes a lot more time.
Why do you think 20 is the number? Is it hardware, or is it power, or is it temperature? Or
It's more hardware limited. Like our understanding of quantum computing is not too advanced, so we don't have the hardware developed enough for.
Okay.
So because the whole point of a quantum computer is that we are basically working on probabilities. Now the biggest thing that disrupts this is heat.
Okay.
So heat causes vibrations, and anything above absolute 0 Kelvin will cause significant vibrations to change how a quantum computer actually processes stuff, right?
So if I had to pin down to one problem, would it be temperature?
Temperature is probably the biggest problem, but we do take care of it, because if you know this or not, most coldest place in the universe is probably sitting in Earth, because we have been able to pull down the temperature in laboratories to millions of degrees from absolute 0 Kelvin.
But it's not scalable. It's just in a small
Yeah,
area.
obviously we can't have a very big area with that limited amount of heat,
So that's the problem.
but it's good enough for whatever we are trying to do, which includes quantum computers. So the biggest issue is interfacing with all the qubits in such a small area at such a low temperature with the current material science that we have. I think that is the biggest hurdle right now. It's not one thing in particular, but a combination of everything.
And I genuinely feel one of the most underrated topics in engineering is material science. Sure, all your designs can be in a laptop, everything you can do with electrical engineering or computer science engineering, but once you want to have like a real world effect and it translates to real life, we need material scientists.
That's true.
So material scientist is underrated engineering level.
The thing with material sciences, it's a lot of working in the background without knowing what's actually happening, because material scientists, they keep working, and 20 years later you have something like silicon coming out. Then there's a whole transistor revolution, and then nothing happens for the next 20 years. Someone finds a phosphorus or a gallium nitride compound that enables blue LEDs.
So basically dependability. Material science
It's
is more
honestly
dependable. It's dependent on the technology at the time.
No, their job is to define the technology at the time. So the thing is, they're not usually appreciated, but their work over time is really what drives us forward, in my opinion.
Yeah, as Shrish mentioned, quantum theory is all about probability, and it's not your normal probability theory which you study with normal uh, what are the numbers we use called Cartesian numbers? No,
Decimal system.
integers. Yeah, it's not a normal probability with integers. I read this line which says quantum theory is a probability theory with negative numbers. Any comments?
This again is
I mean, talk about the amplitude stuff, like square amplitude.
yeah, so that is where we come back to the fact again that there are a lot of things that work out in quantum sense because of the math, but we don't really have an understanding for it, and I think this is a very good example for that.
So we just say that look, the math works out, so it's correct. Even
Precisely.
Pretty much.
Because our understanding of universes working is on the classical mechanics that we have grown up with, that we are accustomed to, right? So we can't get an intuitive sense of what's happening at the subatomic or at the quantum level. So the only thing that is there to guide us through is math, because math works on logic. So even though we can't make sense of an output, as long as we know that, okay, this is what the output for this equation, this function is, and this is what it implies, I have to move ahead with it, and it works most of the time. So that's pretty much what we do. If you do go into it, the probability of an outcome of an experiment, like you said, you got a negative amplitude, right? It's basically called quasi-probability in technical terms. So these are, it's again very hard to explain this without math, but think of these as sort of events that are more unlikely to occur than events that don't occur at all.
Okay.
So, and again come back to, if you really want to make sense of this, we don't usually have a probability function in quantum. In the mathematical sense we do have it, but it doesn't really tell us anything. It's usually the square of the modulus that tells us the probability location, what we call as the chi-square function.
Yes.
So even squaring a negative number, it becomes positive again, and in the end it works out, or we have made it to work out for our intuitive understanding to a level.
Do you feel there's a sense of we are manipulating a lot to satisfy our needs, where it might might be wrong? Like in a sense, like, okay, look, this works out in maths, guys, so it should happen. But even though if it's not experimentally verifiable, so do you feel like there's a sense of being overly optimistic? Or do you feel like, okay, once it's maths, it's done. It's the concrete ground level proof.
Most of what theoretical physics is just math, and experimental physics.
Here's the thing: it's not theoretical physics anymore. It's quantum. It's not classical. It's not integral.
So
It's not calculus.
I think we are mistaking an output for a result. So the difference I'd like to make here is there is no system which just has an input and output.
Okay.
Some processing happens in between. You might know what exactly is happening, you might know a part of it, you might know nothing of it. So our quantum mechanics basically sits as a block over here. So we see an input and we know what output should come from that, and that output does come from that input, but the intermediate states don't make any sense. Mathematically they do, logically they don't. The input and output relation makes sense both mathematically and logically, but the intermediate states don't make sense logically, but they do mathematically.
Okay.
I don't know how clear I am, but basically the point is, think of quantum mechanics as a black box. You see inside the black box and you see something very wild that shouldn't happen, but yet it's happening, you see it happening, and the output works out. And math tells it is supposed to happen, but you still can't wrap your head around it. Negative probability, for example, again, let's say I have some sort of function that gives me a probability output, what the probability of it is, and then I have to say whether I can detect it at some particular space or not. So I look at an input, I say, okay, I have a ball in a room, my output should be that somewhere in this room I should be able to find that ball. And when you put it in, you get a probability of -1. that doesn't make sense to you, but when you square it and when you reach your final output, you get a probability of 1 again. That somewhere in this room I should find this ball. So your input and your output do make sense, but what's happening in between doesn't make sense to you logically because it's happening with quantum mechanics. Mathematics still makes sense. That is why we rely on math so much. Even if we don't understand what's happening, math for the most part is going to make sense of it. Does that make sense?
It does. No,
yeah.
it makes sense. And yeah, as we were saying, quantum probability works on amplitudes. Amplitudes are, can we say amplitudes are square root of probability? Like if you square amplitude, you get probability. You get quantum probability. Is it a correct statement?
I wouldn't call it wrong. I wouldn't call it right either. There are a lot of nuances to it.
Okay.
Because to give you a very simple example, a square root can be positive or negative. That is the simplest example I could possibly put. The second thing is we usually can't represent phase probabilities in terms of absolute functions because probabilities are magnitudes and those magnitudes are derived from some function. So even if I root the probability of existence and I get a graph, that will only give me the magnitude of the function. There are a lot of other things about that function that I need to find out.
Most of quantum maths is done using matrices for the very reason that Sri stated. Like you can't like say it is there, but you can put it through a matrix function and you get like it can be here or it cannot be.
Okay.
To a much more accurate degree.
Because it's a very difficult task. When you initially get started, the math will start making sense to you pretty quickly, relatively speaking. But when you stop and ponder, like, why is this happening? What sense does it make? What does it imply? You get thrown down a rabbit hole very fast because nothing is going to make sense. You initially have to realize what makes sense and what is to be ignored.
Do you think there's some documentation missing? Like how for classical physics you have Newton's work, right? So on that you build literally everything. Would it be helpful if there's one standardized documentation upon which if we can build your like there's a lot of gray areas. You're like, okay, no one understands this, no one understands this. So if there's a set a structure to all these randomness, do you think it would help, or does it already exist, like a set documentation?
I think it already exists, but it isn't identified yet. Because when in the 1600s, when Newton wrote Principia Mathematica, he had no idea that this is going to define all of calculus and physics and math for years to come. And there were a lot of his contemporaries who published equally well written, if not better work. And they were at the starting stages of understanding how things work then. You can understand the person who figured out gravity defined everything he possibly knew, and we started off from there, considering that as base. So in our quantum journey, well, the research has been happening for a long while. Once again, this is not something intuitive, it's mathematical. So it's going to take a lot longer than it took us for regular...
Newton had an unfair advantage that he was working in reality.
Exactly. Yeah. That's a pretty good way of putting it.
So there's a real apple that fell really on his head.
So you can't do that in quantum. You can't ponder about such things. You have to basically ponder on equations and hope they make sense in the end. And there are a lot of works out in quantum. Maybe the work we are looking for, maybe it will be defined 20 years, 30 years, 40 years down the line. Maybe it's being written right now. Can't say that.
Maybe it's already been written, but we don't recognize it as
exactly.
Yes. Isn't... Okay, a little bit off topic, but what's the place where there's a library online where literally every text ever written is already there, but we don't recognize it. We can't... It's just a set of... It doesn't follow set like rules of a sentence, but everything, the knowledge of everything is there in that library.
No,
it's no, it's project okay, but there's a library which literally answers to every question which you can make, which has been made and which will be made. The answers to that question already exists. All we have to do is find where it is in that big text.
Is it Library of Babel?
Yes, Library of Babel. Library of Babel. Check it out. Okay.
Back to topic.
Yeah. So look, now we're not going to. So guys, if who are listening, we're not going to go into like quantum probability and like start talking about numbers. So activity what you guys can do is do the double coin toss experiment with the quantum coin. Like they are similar to online. One very good resource which I use for the research of this episode was what was it by? QSkit? Is that Quizkit.org. They have a really well defined structure, and even they have a simulator for the double coin toss experiment. So in reality, double coin toss is like tossing a coin 2 times and finding out the probability. So what would be the probability of getting heads and tails in normal coin?
50-50.
50-50. But with a quantum coin, what's the probability?
We don't know. Exactly.
Of a double coin toss. It depends on your initial state. Apparently, if you set the initial state to 0, it's always 100% 0 after a double coin toss.
So how exactly are we defining a quantum coin over here? I think before we go into this conversation, for the sake of, if not for the 3 of us, probably the audience, we should go a little bit into what a qubit is and how it actually works.
I was going to bring that up after this.
Completeness.
Because I want to bring it up after this because once you start your learning quantum journey, this is the first one of the first like wow factors you encounter, which makes you want to read more. So I just wanted them to think like, hey wait, how is getting 1 in your coin toss 100%? So
right, I think then I'll leave this to you.
So do the simulation. Go to quizit.org and do the simulation, and you get to know that the end result of the coin toss would be 100% and 0% depending on the initial stages you set. Why is that? We'll cover it in the episode. Hope you're intrigued enough. Okay, why is that? So apparently, if you set the initial state to 0, what do I mean by setting the initial state to 0 is basically before tossing the coin, putting the heads face up. Let's say heads is 0. So putting the 0 face up and you toss the coin. So you might get a 0 or a 1. The probability of that is half and half. And from 0, you toss a coin, you might get a 0 or a 1. That would be half and half. But in a quantum coin, if you start with face 1 and you toss a coin, the probability of getting 0, the amplitude is root 1 by 2, and probability of getting 1 again is minus root 1 by 2. So probability of 0 would be 1 by 2 plus 1 by 2, 1, and probability of 1 would be 1 by 2 minus 1 by 2, that would be 0. So that minus factor is causing is causing you to question your basics of probability. So this property is called interference in quantum mechanics. So yeah, this is one of the most fundamental property that gives a upper hand to quantum computers than normal computers. Why? Because you see like how probabilities cancelled and it gave you a 100% result, and it negated one result and it gave you 100% of one result. Let's say that 100% result was a desired result, right? So this property called the interference would, if you use it to cancel out your wrong answers, which means it would increase the probability of measuring the right answers, is what gives quantum computers the upper hand over classical computers. You guys, I mean, you can discuss, we can edit this out.
No, I think it's more to do with the fact that a quantum computer can work with a lot more states at once.
Yeah, but like you see,
the whole factor of probability cancelling out is just an inherent result of the math.
Yeah, it
is independent of what we are trying to calculate.
Okay.
So any information being added or being removed is totally a function of the math. It's not a function of what I'm trying to find out from it.
Okay, so you don't know what you're trying to find out, but the math is happening.
It's more a consequence than a result.
So think of it as
Okay.
It's a part of the circuit, not a part of the output, the negative. So the whole point of why quantum computers are considered faster in parallel tasks is because, as you said, it can hold some amount of, let's come to qubits, I suppose.
Wait, then let's just flag this part. Unlock your phone.
Okay.
We'll flag this so it'll be easy when I'm editing it.
Okay. Add a flag.
Yeah. Yeah, this one.
Continue, pull it to qubits, I
Yeah.
suppose.
So Shrish, what is qubits? I think it's high time we define a qubit.
Right, so we start off with regular bits. From now on, we'll be calling them classical bits because new kids in town, I suppose. So a classical bit is something that either has the value of 0 or 1. Either there is current or there is no current. Either the switch is on or it's off. It's very clearly defined in the broad sense, and this is what all of our computation is based on. What happens in a quantum bit is this definition between 1 and 0 of this clarity of on and on goes away. It's like dangling that switch. If you remember, as children, we all dangled that switch in between to see where it would turn on and off,
Yeah.
where the fridge light would turn on, where the fridge light would go off, right? It's that, but with a probability function. There is no set point above which something happens or below which something happens. So it's in our hands as to how we exactly define a qubit. But a qubit is something that we call as a superposition, a new word. Something that is 0 and 1 at the same time. So what this enables us to do, for a moment, let's go along with me, just pretend a qubit can be 2 bits at once. So what this helps us to do is exponentially scale up computation when using qubits. So something that a regular bit would require, let's say 2, 4, 8, 16 or 32 regular bits, can be done with log 2 of that. So let's say we have a circuit that requires 16 regular bits, but it would only require log 2 of 16 qubits, which is 4 qubits. So in lower numbers and lower magnitudes, this sounds like a decent improvement, but the larger we go, the heavier the improvement becomes. This is inherently what gives quantum computation its advantage over classical computation.
So at the hardware level, it's using less hardware to do the same task as a
Yes,
classical
because
computer.
it inherently is able to store more information in one bit.
in those same registers. By the way, do they have the concept of registers, and are they different registers, or what's the hardware part?
The hardware part to an extent is there, but the way we have defined it in regular computers doesn't exist anymore because the math doesn't make sense over there. Because it's true that a qubit is more information dense, but that also implies that putting information into it and reading information out of it becomes harder.
Okay.
You can look at a bit and you can tell, okay, this
It's
is
1
0,
or
this
0,
is
yeah.
1. The LED is on or the LED is off.
The
You look
LED
at-
is almost on. The LED is fully
You
on.
can't do that with a quantum bit. You
Okay.
don't know what is happening. And the funnier part is you won't know until you go looking for it, which is what we call as entanglement. Okay, we'll reach that at some point
And
later.
just to mention, Golas mentioned how a quantum computer can only have 20 qubits right now,
Yes.
right? So that might not sound like a lot, but that's actually a lot. That is almost more than a million normal bits.
So the information that can be contained in 20 qubits is almost the
It's
Same
more
as
than
this.
2 power 20 bits.
2 power 20
it's
bits.
2 power
Yeah,
20
that's-
bits, which is more than a million bits.
That's a lot.
Yes.
In terms of computation, 2 power 20 bits is still not a lot. That is why we are struggling. But you do realize with every additional qubit we can add,
It
how
increases
exponentially our
exponentially.
calculation power increases.
So again, at the, do you guys know what's at the base hardware? Like at the end, you guys are going to have. Are you guys going to have gates? Are you guys going to have the classical AND gates or gates? Or
We
you
don't
guys-
have classical gates. We have
We
quantum.
have quantum gates.
The Hadamard gate, the C0 gate, they
So-
work differently than classical gates. Because as Pai said before, in quantum mechanics, you can't work with gates with an, intuitive sense. So we mostly define gates as matrices.
Okay.
Then we pass qubit states, which are again matrices through those gates. It's all just matrix multiplication. A qubit matrix is multiplied by a gate matrix, and you get an output qubit matrix.
Ooh, okay.
This is what we use so that we can make most sense of it, because at this point over the years we have learned to make some sense of the maths as well. If we look at it in purely logical terms or visual terms, if that is even possible,
We
it
won't-
becomes very
we
hard to
won't
understand
understand.
what's happening. It sounds like magic. It looks like magic. The only thing that gives meaning to this madness is math.
Maths ties all the chaos together.
Yeah, we come down to math. you can understand what happens in quantum mechanics at a very brief level without math, but if you ever want to do anything in it or have any sort of meaningful understanding, you very unfortunately cannot do it without math.
What do you think is lacking? Is it a base, like something in fundamentals of maths, or something, some device so that we can
It's
absorb?
not lacking so much as
The best way I would describe this is probably a quote from one of Xavier's videos. Nature's imagination is greater than yours, and she's under no obligation to make herself comprehensible.
Nature's imagination is greater than yours. That's nice.
So the whole point is we are trying to chase something that our monkey brains can comprehend.
Okay.
Something that we are trying to chase wasn't built to be comprehended by our monkey brains. We are trying to go through it, trying to understand what's happening. So we come up with methods that make it clearer for us. What actually happens. There's no language that defines it.
Yet.
Never, probably.
Probably we will. Do you think? What are you saying?
We live in a classical realm. To us, this makes sense. If we lived in the quantum realm, that would make sense, and what we experience now doesn't make sense.
Yeah, what my question was, like, is there a device lacking? Like, is there an Ant-Man device lacking? So where you can just go shrink yourself down. And
even if it's like Ant-Man device.
To save all the Marvel fans, we'll not go into the science of how inaccurate that is.
Okay. But like, just a reference, even if we had the Ant-Man device, we still wouldn't understand the laws there, because they're like...
What if you spend enough time? What if you sit under the quantum tree and a quantum apple falls on your head?
It's not. We don't know if it will hit our head. We don't know if it will come down. Yeah.
It will teleport into your stomach. It will teleport to the next guy, and you
will
teleport on a different tree, and then you'll see the apple growing into a seed, and it will
we don't know what's going to happen.
I guess I triggered the quantum guys. Okay, yeah, just express yourself. Like, what were you saying?
Like, here an apple falls from a tree. For all we know, the apple becomes the apple tree seed in a quantum realm. Like, it goes backwards in time. We don't know what happens.
The point I'm trying to come at is what we are trying to do, at least in this podcast right now, is trying to get an intuitive sense as to what is happening. We are trying to do it without the math. And while everyone says something is impossible until it isn't, I'll go on record telling this: it's impossible to comprehend quantum mechanics without the math. Some things do not make sense to our brain. We are not advanced enough to understand it.
It's and good luck understanding the math.
And that's the part. That's the point where we have math. After a level, math becomes easier than understanding what's happening around. That is where we truly need math, and we use math.
Dude, imagine math becoming easier than what's happening.
Why imagine? It's happening.
It's happening.
Okay. Okay, can we start your project part?
Yeah, I suppose.
Quickly state the title of your project and why, and Sri's your project. This is the title of it. This is your title.
So my project basically revolves around quantum phase estimation. And in brief, what we will do is we'll have a bunch of qubits, we'll put them in superposition, and then we'll find out the phase component of it. How that is helpful and where it goes and what it does, I think will be revealed in due time.
And why?
My project was like implementing a certain quantum circuit using quantum logic gates. Like, ours was a very close approximation to what Grover's algorithm does.
Cool. And guys, from now on, right, I'll try to be at the pace of you guys, because look, you guys did a semester of this and I did 2 days research of this. So stop me where I'm wrong, or correct me or stuff like that. So let's start off with Pi's project. Dude, Pi's project, apparently the appendix and all the extra stuff are more interesting than his implementation.
That's because it's a logical circuit.
I know. Like, okay. In terms of like a podcast episode, you can't make a podcast episode on implementing a circuit. It's better to talk about your.
I like that
algorithm.
challenge. I might start a podcast and do that.
Oh God, can you imagine?
Just
So
for
guys,
that.
can you visualize this game?
No, you don't need to, honestly. I can make it very interesting. I'm pretty sure.
Audio only podcast.
An audio only podcast where you discuss about implement. It need not be a quantum circuit, it can be an electronic circuit. or
How
something, but I'm
would
pretty
dude,
sure.
no one is going to follow after 2 minutes. Like, how are I going to start? So guys,
Are you
visualize.
challenging me?
Add a circuit. No, that's too hard, man.
I'm pretty sure I can do it, but anyways.
Okay, so look, Pi's project is implementing a circuit, but mostly we'll be talking about the Grover's algorithm.
Yeah, sure.
Do you want to say, like, do you want to talk about what are the major application of the Grover's algorithm?
Grover's algorithm is used in like probability stuff, like finding the mean of stuff, and it's a random search algorithm. Like if you give a mass of data randomly, it's a search algorithm that can find what you're looking for easily.
Okay, so
It's capable of that rather.
so basically the has two applications to search unstructured data
Yeah.
fast.
You can call
I
it
mean
that.
you can search without quantum computer, but fast.
Yeah.
But relatively fast. And I mean, people who have done data structures, it's know that that's a good problem to solve finding an unstructured data. And I think the second application would, as you said, it would be to speed up the runtime and run execution time, which and not by a factor of by an exponential factor.
Yeah.
And people who have studied risk architecture, unfortunately, would know that that's a good thing to do. That's a good problem to solve. And okay, is it fair to say that the algorithm can be viewed as a equation solver or a constraint solver rather than finding the solution?
Yeah, you can call it that. Like the circuit, I said, it employs Grover's algorithm to get the output faster than a normal circuit would.
Because like the most advertised application of Grover's algorithm is solving the Sudoku puzzle. Apparently, like solving it is hard, but checking if it's correct is easy, right?
Yeah.
Because you just check row wise, column wise, doesn't repeat. So,
We are going into P versus NP territory right now.
what's that?
You explain.
Okay, so
Briefly.
this again comes into math. In fact, if you think you have a solution, the Clay Institute is willing to offer you $1 million tax free for this. So I think the Sudoku one is the best example. There are a lot of problems where if you have a solution, you can tell if it's correct or not. But arriving to that solution is a much more tedious process. The best example being Sudoku. So this, I think, a part of what Pi is doing is also being researched into trying to solve this, because this problem is a very long-standing problem to say whether everything belongs to P or NP or somewhere in between.
Okay. And the first application, which would be to speed up data, to speed up searching element in unstructured data, would be, like approximately like how much faster could you search an element?
It depends. Like Grover's algorithm works based on an oracle that is created. The oracle depends on how many inputs there are.
Okay.
So like you
So
give,
Oracle, what is Oracle a matrix or is Oracle a function or what
it's a matrix that you make.
Okay.
That is named. Yeah.
So
So like the oracle basically if you give a certain input to the oracle, you always get a specific output. There's no probability in this part. It's just it's the first part of the Grover's algorithm. You pass the input through to get a certain output.
okay.
And that actually simplifies searching by a lot, because like you just because you always know what to expect from the first part.
Okay. I mean, a quick stats which I got from researching on this topic was, suppose if you had to search an element in n boxes, let's say, the average number of boxes you had to search would be n by 2. but if you had to search in n quantum boxes using Grover's algorithm, then the average number of boxes you had to open would be
root n.
root n.
Yeah.
So there's a
Because like
exponential.
you know what you're looking for, so you know what's going to happen at the end of the oracle for that. So you just pass the data that is like you pass data that's going to match that.
Okay.
Like whatever you pass through for the search algorithm, it narrows it down
Oh,
exponentially
so you
because
can't-
you know what is going to come out.
So your input is also controlled.
Yeah.
So you get a better output, or you get a faster output.
You get a
the same
faster
output but faster.
Yeah.
Because your input is controlled or modified, model input. Okay, makes sense. Okay, and limitations, G algorithm. Cool. What do you say? The block diagram of that execution. You said. Could you just briefly put in words your block diagram of executing the Grover's algorithm, and I'll ask you why this.
So the Grover's algorithm, you take the input qubits and then you pass it through a Hadamard gate, which changes the state from like clustered state to what is it?
What is the states? Clustered state, huh?
Superposition.
Yes, clustered state to superposition state.
What would those states be?
So a clustered state would basically be, because I understand why this is difficult. Once again, it's all math, so it's very difficult to put this into words, but I'll try my best. So a clustered state is basically two separate qubits. Let's say if I'm passing two separate qubits through a Hadamard gate, my input would be qubit A and qubit B. Now they are clustered, they are two different qubits, you can tell which is qubit A and which is qubit B. When they come out of the Hadamard gate, they become superposition qubits. So let's say qubit C and qubit D come out of the Hadamard gate. But now it's very hard to differentiate which qubit originated where, or what happened to that qubit so that it reached this state.
Okay.
That is basically what happens.
So
in
what's the
an
favorable
Hadamard
state?
gate.
Is it the superposition state or?
So the issue is most of the computation happens in the superposition state. Because it's more information dense, and it's at the same time it's equally harder to control.
So can we say that we value information density more than ease of decoding?
Because ease of decoding is a one-time thing. Information density is a recurring thing. So something which ought to happen again and again, if I can make that faster, that's much easier for me than going through the pain of having something be simple.
Yep.
Okay, so we pass the qubits through a Hadamard gate, which Shrish just explained, and then we give it to the oracle, which I mentioned earlier. After that, it's passed through Grover diffusion operator, which is a whole lot of math, and then we get our output.
Okay, and like in your block diagram, I see that you iterate the thing root n times. Why would that be the case?
Yeah, that's just like every time you. How do I explain this?
No, but the thing is, my question is, was it a random choice for taking root n, or is
there is a whole lot of math behind the reason.
Okay.
Like it basically Grover, who made the algorithm, did a whole lot of math. You can look up the math. I don't know how to explain it in words,
Okay,
but
so
it gets narrowed down to root n for the most optimal output.
Okay, so the explanation for optimal number of iterations in your appendix is different to this.
It's same concept. It's same concept.
So let's cover that in.
Okay. Then.
Okay, and and as we said, application of the Grover's algorithm is speeding up search and execution time. And one more scenario, one more application would be to solve the satisfiability problem. So Sheesh, could you tell, could you give a real life scenario for the satisfiability problem? What's the problem and a real life scenario?
So I'll start off with explaining the problem. I don't think there's a very practical real life scenario, but I'll try.
Okay.
So the satisfiability problem comes down to again classical computing. So it basically states, given some sort of logic, can there be any set of inputs that define the output to one particular state. So let's say I have some random black box circuit that works in the classical domain, and it has 4 inputs, A, B, C, D, and 1 output, E.
Okay.
So the question goes, is it possible that for any possible inputs of A, B, C, D, which I think is 4 factorial, that comes out to 24. So of all 24 possible inputs, is it possible that the output remains the same, either 1 or 0? So there are this can be proved for various circuits. I'll give you an example. Let's say I have a circuit that says A bar and A.
Okay.
So if the input of this circuit is 1, this circuit simplifies to 1 and 0, which is 0.
0.
If the input of this circuit is 0, then the circuit simplifies to 0 and 1, which is still 0. So irrespective of what the input of this circuit is, the output of this circuit is always 0.
Okay.
So there isn't per se, it's one of the theoretical math problems we have. It's very difficult to pull it into real life. But this basically helps us when we have a lot of constraints. So when the number of constraints we have start to increase, a lot of the algorithms we use for routing, networking, or in graph theory start taking longer time or simply fail. Over there, this helps us a lot. So I'll give you simple real life examples. A more academic example would be routing an FPGA or a PCB. A more real life example would be, say, FedEx has a network and then there's a snowstorm, so 5 of the routes are blocked out. Okay. So you can update this into your network theory or graph theory, and then it's going to spit you a new output. But this computation cannot be done dynamically for most cases. So over here, I don't know how accurate this is because I'm making this up as I go from my understanding. But places like this is where the Boolean satisfiability problem comes in. So because a Boolean satisfiability problem in essence works backwards. It tells you that I have a fixed output. Now let's design a system in such a way that irrespective of what the inputs are, I always end up at this output.
So
if that is one way of looking at it.
Okay, so you have the desired output, you know the input, and you're constructing.
You don't know the input. You're preparing for every possible contingency of the input.
So okay, so you have a desired output, and you're trying to create an environment with those parameters, so that what input you give, you get the desired output.
Because in typical design, we work forward. We have a set of inputs. We say, okay, this has to go here, this has to work with this, and then you check at the output. Over here, we are working the other way around. We have a set output, and we say, irrespective of what the inputs are, we have to arrive at this output, and let's design a circuit in such a manner.
And is this a ongoing problem, or has it been solved?
It has been classified as an NP problem.
What does that
from
mean?
my knowledge? Basically, it is doable. So it's one of those problems where, if I'm not wrong, I'm really not very sure about this, but it's one of those problems where if you have it done, if you have a circuit, you can verify if it's true or not, but getting to that state is very hard. Like we talked about Sudoku. So solving a Sudoku is a hard process, but once you have the Sudoku solved, you can verify it pretty quickly. Yes. It's the same thing. If you have a circuit, making the circuit is a hard process. But if you have that circuit, you can loop through all possible input sets and see if the output is the same.
So that would be the satisfiability problem.
Boolean satisfiability problem, to be specific, just in case there is some other domain with some other satisfiability problem that I'm not aware of.
Okay, cool. And right, there's a section in appendix that says for a quantum experiment, the optimal number, there's a set optimal number of iterations. You have to set minimum number of iterations you have to carry out for getting the desired output, and you have given it a value of,
it's pi by 4 root 2 power n.
Why would that be the minimum number of iterations?
It's not a minimum number of iterations so much as the optimal number, because like when you're getting outputs for quantum circuits, there's no guarantee that you're getting a set output as of yet.
Okay.
So it's like you might think that giving more and more number of iterations you will get a more accurate value, but the chance of success is not monotonically increasing. That doesn't means it's not increasing the same amount every time you run
So
it.
basically, it's not the more number of tries, the more accurate.
Yeah,
not that.
it will be more accurate, but the increase in accuracy isn't that noticeable after a point.
What? Just a top some problem.
It's not linear. That's
It's
what
not
I'm
linear.
It's not linear. So like if you half the chance, if like I said, it's pi by 4 to root 2 power n. If I were to half it, that doesn't mean that like I get
Half the.
yeah.
Yeah. You won't. Okay.
It's not guaranteed that the chance drops down to 50-50. It might drop down more or it might drop down less.
Yeah. And is it a? Can it be functionalized? Like, can we say it's an exponential function or it's a?
You get an asymptotic curve if you were to plot it on a graph. Like it tends to a particular value, but it never reaches it. Kind of.
That value being peak 100% accuracy.
Yeah.
Which is not achievable.
For infinite iterations, it is, but in all practicality, it's not. We can get pretty close to it, but we never can reach it.
Yeah.
Just
So
like
the
an
number of
asymptote.
so the number of iterations gives you a pretty accurate one, and it's not infinite.
Fine.
Like,
It's
there is some margin of error.
It's accurate enough.
Yeah, it's accurate enough for an output.
That's cool. And yeah, one of the most interesting slash cool application of your project, according to me, obviously, was the use of Grover's algorithm for brute force attack of AES system. Could you just first before that, could you just briefly describe what AES is in terms of cryptography?
AES is the most commonly used internet encryption cipher right now. Like, your internet connections are encrypted, right?
Okay.
They are done mostly using a 256-bit AES encryption.
Okay, so it's is it an encryption standard or is it a algorithm?
It's an algorithm that is used as a standard.
It's a standard algorithm.
Yeah.
AES 256. Okay. So
Like we discussed earlier, Grover's algorithm is a unstructured search algorithm. So it can brute force basically any type of encryption.
yeah, we mean it can basically try out all the
Yeah,
combination
it just
of passwords.
keeps trying out all combinations till it arrives at the last one, and it's significantly faster than most other methods.
And what does it mean when we say AES is a symmetric algorithm or a symmetric encryption?
So symmetric encryption means like if you give an input, you get an output. If you give that output as input, you should get the same what your original thing was. So for example, if you give A and you get say D, if you give in D, you have to get A.
That's what symmetric means.
Yeah, that's a symmetric encryption.
Okay. And in lines of cryptography, since the introduction of quantum computers and new quantum algorithms, now the encryption services has another headache of making the encryption algorithm quantum resistant. Is that
That is something that people will have to do, but I don't think it's an immediate threat because we discussed earlier the difficulties in creating a quantum computer and running it. So it will be needed, but I don't think it's too much of an immediate need.
and and why is AES 256 considered quantum resistant?
I don't know that.
It is just more computationally complex. Our current quantum computers aren't there yet. It's quantum resistant to our current gen technology, not quantum resistant as a whole. Because the whole point of AES encryptions and most encryptions for that matter is factoring a really large prime number.
Okay.
So we have something called as Roy-Strosa algorithm. I'm not sure. Please don't quote me on that.
Okay, so we have realized something. We have experienced a minor hurdle. We have lost 30% of the podcast, the end part. So the bright side is it's just 30%. So let's do it all. Let's do it again. And these are the times when I miss Srini. Man usually takes care of stuff like this.
Shane is probably listening to this laughing.
Yeah. Oh God. Okay. The thing that pisses me off is, look, this is, first of all, this is a very hard episode to research and record on, and the basic requirement would be continuity, and even that is broken. But game's a game. We gotta do what we gotta do. You just gotta keep living, man. Matthew McConaughey style. But anyway, so we'll try to keep the continuity going on, and I think we stopped with Shrish explaining Dilshah's algorithm. So Shrish, take it away.
Great. So I think I was talking about the prime factorization. So coming back to it, most encryption, including AES, is based in factorization of really large prime numbers. So there are quantum-specific algorithms that make this process a lot faster. So this essentially disrupts the whole point of it being a difficult process and makes the encryption crackable in a meaningful time. So AES 128 I think can be cracked, and 256 we aren't there yet computationally, but I'm pretty sure we'll reach there in a very short time. And if and when we do reach there, there will be some challenges associated with it, but I'm pretty sure we will have better solutions by that point.
And give me a sec. Yeah, and while going in these lines, and you encounter different topics like quantum cryptography and quantum key distribution, which would which are very interesting, but further discussion would derail the purpose of, would derail this episode, and like it would go into topics like encryption, cryptography, blockchain, and stuff like that. So we leave it up to you guys. If you're curious enough, pursue the research and go forward. So wrapping things up, we'll move on to Shish's project. So Shish, state the title, your conclusions, your results, and what you did.
Right. So my project basically revolved around quantum phase estimation. I had a circuit. I put in a bunch of qubits into that. Some things happened, those qubits got superpositioned, and I got an output qubit, and I took one particular state of that output qubit, which we call as a phase. It's pretty mathematical, but I'll try my best to stay clear of it for your sake and for my sake. Do forgive me if I delve into it from time to time because it's pretty hard. So, before we actually go into what I did for my project, let's look at what needs to be built up for this project and what this project leads up to. So, an essential part of my project was something called as a quantum Fourier transform. Most of us could be aware of what a Fourier transform is. It's basically converting a signal from time domain to frequency domain. And why is it required? It's used almost everywhere around us because most of our sensors give us inputs in analog forms. However, the processing that occurs on it by computers or embedded system is in digital. So we need to convert the analog signal into digital signal, process it, and then probably in more cases than not convert it back to analog for someone to view it or to comprehend it. Now, quantum Fourier transform is the same thing as a Fourier transform, just using a different algorithm, which runs a lot faster because Fourier transform is again one of those algorithms which benefits a lot from parallel computing because the outputs are independent. So in simple terms, if we talk about it, a regular Fourier transform for say n bits would take n times 2 power n gates. However, a similar algorithm in with regards to quantum gates would only take n square gates. So there's a huge difference over here where we are raising n to the power 2 for a quantum algorithm, but we are raising 2 to the power n, which is significantly exponentially larger than n square. The second thing, interesting thing that we found out in quantum Fourier transform. So I'm once again not delving into the math, but some interesting things we found out in the research doing so. So a part of quantum Fourier transform basically involves interaction of all bits to one specific bit. So let's say there are 4 bits, right? And
When you say interaction between bits, do you mean like physical interaction or what do you mean when two bits interact?
Okay, right.
Two
So
quantum bits interact.
the interaction between 2 quantum bits, you're talking in terms of physical or mathematical, right?
Yeah.
So they both lend into each other in a very beautiful way. That is what I'm trying to get at. Let me, I'll finish this and then we'll come back to
Okay,
this
cool.
question, right? So for now, let's think in a purely mathematical sense. I have 4 input bits, Q1, Q2, Q3 and Q4. So Q2 has to interact with Q1, Q3 has to interact with Q1 and Q4 also has to interact with Q1. Some mathematical interaction, we are not concerned with it. Now, as we keep going for higher bit systems, say there are 5 bits, 6 bits, 7 bits, 100 bits, the further we move away, so the effect diminishes with the further we move away. So an example would be the effect Q5 has on the final interaction by interacting with Q1 is much more greater than the effect Q10 or Q20 has interacting with Q1.
So there'll be a so the more further you go away from a reference bit, or let's say a starting bit, there'll be a sense of okay, whatever effect it has, it doesn't matter. What it doesn't change.
So after a point, it becomes so negligible that we can ignore it altogether. Now, this is in the mathematical sense. Now, when we come to the physical sense, where we actually have to make those qubits interact, it's obviously difficult for 2 qubits that are placed far apart to interact compared to 2 qubits that are nearby. So this works out in the physical sense as well, because we don't really need to bother with qubits that are really far apart, because firstly, it's much more harder than qubits close by, and it has a far smaller impact on our final output, right? So this is what our program builds up to. So to understand what our program does, we'll need to refer to something as an eigen equation. So let's say I have a variable. That variable can be anything. It can be a number, x, y, z, a matrix, a quantum state, which is enacted upon. Let's actually take an example. I think this would be a better example. So I have a unitary matrix U that acts upon my quantum state psi, such that my output is my same quantum state psi multiplied by some factor. So when an equation is of this form, where any operator identifying in a state gives you the same state multiplied by some factor, it's called an eigenequation. Now, for our equation, this constant, we have substituted this as e power 2 pi I theta, for the simple reason that it covers most of the numbers in our complex and regular plane.
E power I theta is a form of a circle, right?
Correct. That's a form of a circle. That's another way of looking at it. So over here, this theta is essentially what we call as our phase and what we are trying to find out. This will be the mathematical sense. Now, to make some meaning out of this madness, I'll try explaining this in a physical format. So assume you have a sphere and there's an arrow that originates from the center of the sphere and goes to the edge of the sphere, the surface of the sphere.
From the inside.
From the inside. So now this arrow represents your quantum state. So if this arrow is pointing due north, we call this state 0. And if it's pointing due south, we call this state 1. Now,
and anywhere between that would be?
Anywhere between that would be a superposition of states, what we basically refer to as a qubit. Some combination of both 0 and 1.
Oh,
right?
So is it correct to say that there are infinite number of quantum states?
Yeah, that's correct. There are infinite number of quantum states. We can't filter it down. So now let's assume that there is some arbitrary quantum state and this arrow is pointing somewhere inside the sphere. Now this arrow is going to make an angle with something, either the x-axis, the y-axis or z-axis, right?
Yeah.
So this angle is basically what we are referring to as our phase.
So like in normal geometry, you have like fixed x, y, z. So in quantum, is there a fixed axis or it just varies?
For our reference, we are taking a fixed x, y, z.
Okay.
So now the e power I theta term, this theta is the same theta that we are referencing to. And for future reference, if we ever do bring this up again, this representation is called a block sphere, representation of a qubit.
Okay.
So now this is what we did basically. We took a bunch of qubits, we passed them through a Hedman gate to entangle them. We applied a Fourier transform, we did some processing, and then we passed them through a Hedman gate again to make them readable, to pull them out of the superposition state, and then we figured out the phase value, and that is our quantum phase estimation. Because we have to understand that the moment I look at a qubit to find out its phase, the qubit collapses, it no longer exists. So my knowledge of that phase becomes immaterial. So I can only, but if I have to work with that qubit, I should know what its phase is, what its properties are. So based on the formula, how that qubit was formulated, I need to feed it to some sort of mathematical algorithm that gives me a good estimate of what the phase is or what the phase will be of that qubit. That is what quantum phase estimation does.
Okay, now, so once you have found out the phase, what can you use with that information? What can you do?
Right. So where does this lead to then? So this will again loop back to what I talked about Shor's algorithm and Grover's algorithm, because quantum phase estimation is a very essential part of Grover's algorithm and Shor's algorithm. So you see this whole process repeats. You couldn't have called everyone else. There was another friend of ours who basically worked on Fourier transforms. So his work on Fourier transforms basically enabled us to do phase estimation. Our work on phase estimation enabled Pi to, get along with Shor's algorithm and Grover's algorithm. So it's just like regular circuits, regular computing. You have classical circuits that lead up to gates, which lead up to memory modules and cache and RAM, and then you make CPUs and GPUs out of that, and that makes your whole hardware. And then you go into OS, and it keeps going up and up. So there's a lot of levels below us, a lot of levels above us. We are somewhere sitting in between.
What was that? There was a term for it. I think abstraction hierarchy or something like that.
Yeah, basically abstraction hierarchy, that's it. So, I mean, I don't know if that term would be grammatically correct to be used for a quantum case, but yeah, the logic remains the same. That is how it works.
So, that would be a project. So
yeah, I think that concludes the project. I mean, there were a lot of other mathematical nuances. Some of it was done on hardware, some was simulated on Qiskit, some on the IBM launches, some were implemented in Verilog and C and FPGAs. But in general, without delving a lot into what the math is and how it operates, this would be a good understanding of what exactly a project does.
could you tell a few project titles from the class of other teams?
Most of the teams, so how the project went around is no one particularly had a specific topic to do. Everyone was given a circuit and it was their job, because obviously they were given a circuit and they were asked to implement it. But bare minimum gets you bare minimum grades. So what most of us were supposed to do was understand what the circuit does and write about it. So even I got a circuit, I had to study it to figure out, okay, this is a quantum phase estimation circuit.
Okay.
So different people had different things. Some people had to work with sensors and actuators like OLEDs and buzzers and loading things to cloud and stuff like that. Other people worked purely on different algorithms. Some worked on the Doyle's algorithm, some worked on Shor's, Grover's algorithm, right? And that was Pi. Yeah, that was Pi. Some people worked on Fourier transform, some people worked on inverse Fourier transform, quantum phase estimation. So it's basically a bunch of different algorithms, and everyone is supposed to implement it and figure out what exactly the circuit did and what they are trying to implement.
Cool. So to wrap things up, what would be your one piece of, let's say, advice to someone who's considering taking quantum as a course in the college?
I mean, the biggest issue with quantum is that the eureka moment where everything starts clicking in is very delayed compared to any other course. So things don't make sense initially, and they won't make sense for a very long time, which dissuades a lot of people.
So patience is a key.
Patience is definitely a key, and I would say to most people who are trying out quantum, you may or may not like it, but you cannot take that call before you hit your eureka moment when things actually start clicking in. because it sounds hard to imagine, but it sort of does make sense where your understanding of the world will start to be limited by math because your logic is no longer supporting you. I think a good example of this would be learning about basic variables. When we were first taught about variables in, say, 7th grade or 8th grade, at that point, when you had to find out x, you weren't concerned with the variable x in itself. You were concerned with how many apples in the basket, how many days of work, how many liters of water flowed through, right? It wasn't a tool for you, it was something you had to find out. And then over time, you made x your tool, and now you can substitute x for anything. It can be a word for all you care.
Yeah, like our like a teaching system which was used was like a mapping function. Okay, so 5 apples is this, so this means 5.
Exactly.
6
And
means
that
this.
map wasn't very conclusive because it couldn't, you don't expect it to include everything, and it couldn't. So it started from what it knew. Like today, you can use x as iota, root of -1, but teaching yourself at 7th grade root of -1 apples made no sense, right?
Yeah.
So that's one thing we have to understand. So similarly, the same process happens for quantum as well. You start being limited by your imagination, and it's math that drives you forward. And it's very hard to wrap your head around it. Initially, people think something's not right because we went through this stage a long while ago. And when this stage rears its ugly head again, people think that, okay, something's going wrong, this is not for me, let's quit. So to everyone who does want to try it out, I would really advise you to stick it in for a while. Reach a eureka moment when things start clicking in, because it's an exponential curve. Once things do start clicking in, a lot of it is going to click in very soon, and things will start making sense, and you can't run away from math. Even if God himself comes down and tells you you don't need maths for quantum, I'm telling you right now, you're going to regret it. If you're taking a course in quantum, you have to be comfortable with math, or you have to be willing to put up with it to the very least, because it's the only thing that's going to drive you forward and give you any sort of understanding as to how things work. I think that's about it.
I mean, look, as I mentioned before, I haven't taken a course in quantum. I merely like had 2 or 3 days of research in this field. But like my 2 cents would be, is there a sense of like when you're studying quantum, it's like you're a gambler. Suppose in the future quantum works out, you'll be celebrated. But in case we never cross that hurdle of the black box hurdle, then is there's a sense of, okay, I lost all my research time, I could have devoted it to something better?
I mean, that honestly depends, and this might go a little bit into philosophy, but that depends on what you're looking for. Because firstly, it's not a question of if, it's a question of when it's going to happen. Maybe it's going to happen in your lifetime, maybe it's going to happen the next lifetime, maybe the lifetime after that, but it's definitely going to happen.
Yeah, so if you're just satisfied by, okay, it didn't happen in my lifetime, but I contributed, you guys can
And
go.
obviously someone has to contribute for it to reach that stage. If you think about it, people have been contributing here and there to quantum algorithms all the way from 1970s. That doesn't imply that 50 years of work didn't result into anything.
Yeah.
Because until you reach that tipping point, that pushover point where something great happens, it's all just constant contribution, and no one knows where that point is until we actually reach it. So things might work out, they may not work out, but at the end of the day, you would have contributed something and you would have made a living out of it. You wouldn't have to struggle for basic needs. If you are satisfied with that, then sure, go ahead.
Yeah, I think that wraps up this episode. Thank you guys for being here, and yeah, thank you for your patient listening. All your support is much appreciated, and hope we made you curious enough to do some research on this topic and see where it takes you guys. So yeah, thank you for listening. Keep walking in the free world. Bye bye.